Okay, this is section 13.2 and this is example 3. And we've already taken a look at a couple line integrals, and yet there are other renditions of line integrals. So that's what we're going to talk about in this example. You can see by our definitions here that we may find it common or useful to integrate with respect to x and y together. And this is a little bizarre. We have definitely not done something like this before. Sometimes it makes sense when you're looking at a line integral where you have x's and y's and everything's kind of jumbled up to integrate with respect to x only. So convert everything to x's, or it might make sense to convert everything to y's, or it might make sense to just convert everything to t's so that it's of maybe a third parameter. It just depends on the problem. And I want to try to help you see the benefits of each. And when it maybe helps to do one versus the other. So let's go ahead and dive into example 3 and see the impact of both our paths and what it means to integrate in terms of different variables. Okay, so in this example, we're going to take a look at this line integral, and we're going to look at 2 points on a plane. So our 2 points are going to be -5, -3, so maybe approximately here, and 0, 2, so maybe about there. And we're going to take 2 different paths to get from these two, to get between these 2 points. So the first one is going to be just the straight line from -5, -3 to 0, 2. And then the second one is going to be this parabola, which looks something like this. And we're going to see if these are different or the same. We're also going to look at a couple different approaches to find this. So for our first part, for part A, we're going to look at C1, just that line segment. Okay, we could pretty easily just come up with the equation for the line. So the slope of the line is 2 minus -3 divided by 0 minus -5, and we get 1. And if we use our second point there, we have the line y minus 2 equal to 1 times x minus 0. So we have y equals x plus 2. And it would make some sense maybe just to take our original line integral and convert everything here in terms of x, because we have y equal to x plus 2. We have dy dx equal to 1, which means that dy is equal to dx, and we can basically go back up to this equation and we can do a full substitution so that everything is in terms of x. So if we do that, our limits will be from -5 to 0, and y squared is now going to be x plus 2 squared. dx we don't have to change at all, so I'm substituting for y, so y is going to be x plus 2. dx don't have to do anything with. The x right here, we don't have to do anything with that, so plus x. And then the dy, that dy is the same thing as dx, so we're going to substitute and put in dx. And then let's take a minute and just distribute this all out and combine. So what we get is x squared. We're going to get 4x out of this, and then we're going to add, so out of here, this distribution, we get 4x, and then we get a plus x. So we're going to have 5x, and then we'll have a plus 4, and we can move that dx out to the front. Okay, I'm going to pause for a minute and work through the problem, and then I'll come back. Okay, so here's the antiderivative. We're going to evaluate the upper value minus the lower value, and what we get is -5/6. This is the value of that line integral. And that was not too bad of a technique to take. So certainly in this kind of a context, our integrand up here, the y squared and the x, not too difficult. It was pretty easy just to convert everything to x and find the answer that way. That's perfectly acceptable. I do want to show you, however, how to turn this all in terms of t, so that you have that as an option, because it might help you depending on the problem. So let's do the same thing, same exact part. We're still doing part A, except we're going to take a different approach. We're going to use a parameterized equation for a line segment. So we're going to do this in terms of t. And as a quick review, we have segments from chapter 9, chapter 10, 11, when we talked through all that stuff. When we did lines, we just made it a segment by restricting what t could be. And what we need to do that is a vector. We called that vector AB, and then we need, that was the slope of the line, and then we need some sort of point, and that point is some initial x and some initial y. So if we're going to go from -5 to -3, and then we're going to go to 0, 2, then our vector is going to be 0 minus -5, so 5, and 2 minus -3, so 5. And then the point is going to be the starting point, which is -5, -3. The equation for x will be the initial x plus a times t, and y will be the initial y plus b times t. And then remember, if we are wise and choose the vector and the point just like I've shown you, so we do the vector between the points and we pick the first point as the point, then t will always be between 0 and 1 for that line segment. And again, just go back to our old notes for that. We don't want to take too much more time than we just did to go through that. Okay, so in this particular case, then our x will be -5 plus 5t, and our y will be -3 plus 5t. The differential dx will be equal to 5 dt, and dy will be equal to 5 dt, and hopefully that wasn't too fast. So basically we're just taking the derivative with respect to t, and then we're moving the dt over. So we're separating the differentials here so that we can make our substitutions into the original line integral. So our line integral was y squared dx plus x dy, and we're going to convert the whole thing to be in terms of t. And remember, we're going 0 to 1 because that's our segment. Y is going to be -3 plus 5t, and we're squaring that. Dx is 5 dt, and x is -5 plus 5t, and dy is 5t. So again, everything that we have in the original line integral, each element is going to be substituted based on our variables t that we've set up here. We're just going to plug them all in. So now everything is down to one variable, and we can find our antiderivatives, and we can calculate the definite integral. Okay, I'm going to pause. I'm going to simplify all this stuff, and then we'll find our answer and see if it's the same. Okay, so here's our simplified integral. If we combine our terms, we distribute everything, move the dt out. So again, we just kind of work through it all, and we do in fact get exactly the same thing. So it doesn't matter if we used x or if we used t. I think using y in this kind of situation would be a little bit tricky, but we can certainly do it. So there you go. There's a couple options there. I would not recommend doing it two different ways. I think the one with x was perfectly fine. I just want to make sure that you have multiple options to use. Okay, now what we're going to do is take a look at part B. And part B in this example is, again, let's go back up to our picture here. So it's the exact same path, excuse me, exact same 2 points, but totally different path. And what we're going to find is that in some cases, this is going to give the exact same value, which is very unique and very interesting. And many other times it will give a different value for the line integral because the path typically does matter. So in this case, we're just going to calculate this one and see if it's the same or different. We have x equal to 4 minus y squared. We're not going to take multiple approaches here. We're just going to go ahead and put this whole thing in terms of probably y here would be the easiest. So dx dy is equal to -2y, and that will give us dx equal to negative 2y dy. So if we start with our integral, we have y squared dx plus x dy, and we're going to convert everything to be in terms of y. Now this means we're going to go from negative 3 to 2 this time, and y squared does not need to change. However, dx is negative 2y dy, and then x needs to change. X is going to be 4 minus y squared, and dy does not need to change. So there we go. Everything is in terms of y. So I'm going to pause this. I'm going to rewrite everything out and do the antiderivative. Okay, so here's our antiderivative after we simplify a little bit, and you can see that our answer here is very different than part A. In fact, this one's positive, the other one's negative, so there's a lot of differences here. So clearly the path between these points matters, but in this case we had an example where we did in terms of x, we did an example in terms of t, and then in terms of y. So you can see that basically the three renditions of what we have here. Okay, so we're going to stop this video and we'll do the next example on the next video.